Hello, this is Tim Smith, the Academic Sport Coordinator for St. John's River State College, St. Augustine campus. This lesson is part 2 of functions of two or more variables and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view functions of two or more variables part 1 prior to watching this video. In this video, we will discuss second-order derivatives, rate of change, differentiability, chain rules, and implicit differentiation. Given a function of two variables, z equals f of xy, if the first-order partial derivative exists and it is possible to differentiate each with respect to x or y, the result is four second-order partial derivatives. The second partial derivative of f with respect to xx equals the partial derivative with respect to x of the partial derivative of f with respect to x of xy, which equals the partial derivative d dx times the partial derivative dz dx, which equals d2z dx2. The second partial derivative of f with respect to y equals the partial derivative with respect to y of the partial derivative of f with respect to y of xy, which equals the partial derivative d dy times the partial derivative dz dy, which equals d2z dy2. The second partial derivative of f with respect to xy of xy equals the partial derivative with respect to y of the partial derivative of f with respect to x of xy, which equals the partial derivative d dy times the partial derivative dz dx, which equals d2z dy dx. The second partial derivative of f with respect to yx of xy equals the partial derivative with respect to x of the partial derivative of f with respect to y of xy, which equals the partial derivative d dx times the partial derivative dz dy, which equals d2z dx dy. These last two are called mixed partials. For example, find the second-order partial derivative of the following functions in two variables. F of xy equals 6x squared minus 8xy plus 9y squared. For the first partial derivative of f with respect to x, we consider the y terms as constants. Therefore, the derivative of 6x squared is 12x, the derivative of negative 8xy is negative 8y, and the derivative of 9y squared is 0. For the first partial derivative of f with respect to y, consider the x terms as constants. The first term is a constant, making its derivative 0. The derivative of negative 8xy is negative 8x, and the derivative of 9y squared is 18y. For the second partial derivative of f with respect to xx, we start with the first partial derivative with respect to x and consider the y terms to be a constant. The derivative of 12x is 12. The derivative of negative 8y is 0. For the second partial derivative with respect to xy, we start with the partial derivative with respect to x and consider the x terms to be constants, giving us negative 8. The second partial derivative with respect to yy, we start with the first partial derivative with respect to y and set the negative 8x term as a constant. The derivative of 18y is 18. Finally, the second partial derivative with respect to yx, we set the 18y term as a constant. The derivative of negative 8x is negative 8. Note that the two mixed partial derivatives are equal. For a function y equals f of x, then change delta y in y from x sub 0 to x plus delta x is delta y equals f of x sub 0 plus delta x minus f of x sub 0. For a function in two variables, z equals f of xy, with domain D, let x sub 0 y sub 0 be an interior point of D, and let delta x and delta y represent changes in x and changes in y respectively. if delta x and delta y are chosen so that the point x sub 0 plus delta x, y sub 0 plus delta y is also in D, then the change in z, denoted by delta z, is defined as delta z equals f of x sub 0 plus delta x, y sub 0 plus delta y, minus f of x sub 0, y sub 0. For the following function, z equals f of xy, find the change in z. Z equals x squared plus y squared from 1,3 to 1.1, 3.2. Delta z equals f of x sub 0 plus delta x, y sub 0 plus delta y, minus f of x sub 0, y sub 0. Apply this to our original equation to get x sub 0 plus delta x squared plus y sub 0 plus delta y squared minus x sub 0 squared plus y sub 0 squared. Next, we let x sub 0, y sub 0 equal 1, 3, and x sub 0 plus delta x, y sub 0 plus delta y equals 1.1, 3.2. Delta z equals 1.1 squared plus 3.2 squared minus 1 squared plus 3 squared. Simplify to get 1.21 plus 10.24 minus 1 plus 9. This equals 11.45 minus 10, which equals a change in z of 1.45. Let z equal f of xy be a function of two variables whose domain is D. Let x sub 0, y sub 0 be an interior point of D, and let delta x and delta y be chosen so that the point x sub 0 plus delta x, y sub 0 plus delta y is also in D. If f is differentiable at a point x sub 0, y sub 0, then the differentials dx and dy are defined as dx equals delta x and dy equals delta y. The differential dz, also called the total differential of z, equals f of xy, and x sub 0, y sub 0 is defined as dz equals the partial derivative of f with respect to x of x sub 0, y sub 0 dx, plus the partial derivative of f with respect to y of x sub 0, y sub 0 dy. Under suitable conditions, the definitions and theorems for differentiability of a function also apply to functions of three or more variables. dw equals the partial derivative of f with respect to x of x sub 0, y sub 0, z sub 0 dx, plus the partial derivative of f with respect to y of x sub 0, y sub 0, z sub 0 dy, plus the partial derivative of f with respect to z of x sub 0, y sub 0, z sub 0 dz. For example, find the differential dz of each function. First, z equals x squared plus y squared. Remember that dz equals the partial derivative of f with respect to x of x sub 0, y sub 0 dx, plus the partial derivative of f with respect to y of x sub 0, y sub 0 dy. In this example, we first take the partial derivative with respect to x, holding the y term as a constant to get 2x dx. Then, for the second term, the partial derivative with respect to y, we hold the x term as a constant to get 2y dy. In another example, z equals x sine y plus y sine x. For the partial derivative with respect to x, we hold the y terms as constant to get dz equals sine y plus y cosine x dx. Then for the second term, the partial derivative with respect to y, we hold the x terms as constant to get plus x cosine y plus sine x dy. Next, find dw for w equals x e to the yz. dw equals the partial derivative of f with respect to x of x sub 0, y sub 0, z sub 0 dx, plus the partial derivative of f with respect to y of x sub 0, y sub 0, z sub 0 dy, plus the partial derivative of f with respect to z of x sub 0, y sub 0, z sub 0 dz. For the partial derivative with respect to x, we hold y and z as constants to get e to the yz dx. Then for the second term, the partial derivative with respect to y, we hold x and z as constants to get plus xz e to the yz dy. For the final term, the partial derivative with respect to z, we hold x and y as constants to get plus xy e to the yz dz. For differentiable functions, the chain rule applies. If x equals x of t and y equals y of t are differentiable functions of t, and if z equals f of xy is a differentiable function of x and y, then z equals f of x of t, y of t is a differentiable function of t, and dz dt equals the partial derivative dz dx dx dt plus the partial derivative dz dy dy dt. This is called chain rule 1 and extends to functions of more variables. Generalized is z equals f of x sub 1, x sub 2, and so on to x sub n. Then dz dt equals the partial derivative dz dx sub 1 times dx sub 1 dt plus the partial derivative dz dx sub 2 times dx sub 2 dt plus and so on until the partial derivative dz dx sub n times dx sub n dt. For example, find dz dt using chain rule 1 for z equals x squared plus y squared, for x equals sine t and y equals cosine 2t. To review, dz dt equals the partial derivative dz dx times dx dt plus the partial derivative dz dy times dy dt. The partial derivative dz dx equals 2x. dx dt equals cosine t. The partial derivative dz dy equals 2y, and dy dt equals negative 2 sine 2t. Put them together to get dz dt equals 2x cosine t minus 4y sine 2t. Replace x and y to get 2 sine t cosine t minus 4 cosine 2t times sine 2t. Let z equal f of g of uv, h of uv be the composite function of z equals f of xy, where x equals g of uv and y equals h of uv. If g and h are each continuous and have continuous first-order partial derivatives at a point uv in the interior of the domains of both g and h, and if f is differentiable in some disks centered at the point xy equals g of uv, h of uv, then the partial derivative dz du equals the partial derivative dz dx times the partial derivative dx du plus the partial derivative dz dy times the partial derivative dy du, and the partial derivative dz dv equals the partial derivative dz dx times the partial derivative dx dv plus the partial derivative dz dy times the partial derivative dy dv. As an example, find the partial derivative dz du and dz dv using chain rule 2 for z equals x squared plus y squared, and x equals u e to the v and y equals v e to the u. First, the partial derivative dz du equals the partial derivative dz dx times the partial derivative dx du plus the partial derivative dz dy times the partial derivative dy du. Therefore, the partial derivative dz du equals 2x e to the v plus 2y v e to the u. Replacing x and y gives us the final answer 2u e to the 2v plus 2v squared e to the 2u. The partial derivative dz dv equals the partial derivative dz dx times the partial derivative dx dv plus the partial derivative dz dy times the partial derivative dy dv. Therefore, dz dv equals 2xu e to the v plus 2y e to the u. Replace x and y to get 2u squared e to the 2v plus 2v e to the 2u. Implicit differentiation for a function with two or more variables can take one of two different formulas. For a function in two variables, we use formula 1. Suppose f is a differentiable function at y equals f of x is a function defined implicitly by the equation f of xy equals 0. Then dy dx equals negative the partial derivative of f with respect to x of xy over the partial derivative of f with respect to y of xy, provided the partial derivative of f with respect to y is not equal to 0. For a function with three variables, we use formula 2. Suppose f is a differentiable function at z equals f of xy is a function defined implicitly by the equation f of xyz equals 0. Then the partial derivative dz dx equals the negative partial derivative of f with respect to x of xyz over the partial derivative of f with respect to z of xyz. The partial derivative dz dy equals negative the partial derivative of f with respect to y of xyz over the partial derivative of f with respect to z of xyz, provided the partial derivative of f with respect to z is not equal to 0. As an example, find dy dx for the function f of xy equals x squared y minus y squared x plus xy minus 5 equals 0. Remembering that dy dx equals negative the partial derivative of f with respect to x of xy over the partial derivative of f with respect to y of xy. For this function, the partial derivative of f with respect to x equals 2xy minus y squared plus y, and the partial derivative of f with respect to y equals x squared minus 2yx plus x. Combine these two to get our final answer, negative 2xy minus y squared plus y, all over x squared minus 2yx plus x. As another example, z is a function of x and y. Find the partial derivative of z with respect to x and the partial derivative of z with respect to y for the function f of xyz equals xz plus 3yz squared plus x squared y cubed minus 5z equals 0. The partial derivative of z with respect to x equals negative the partial derivative of f with respect to x of xyz over the partial derivative of f with respect to z of xyz. Therefore, the partial derivative of z with respect to x equals negative z plus 2xy cubed all over x plus 6yz minus 5. The partial derivative of z with respect to y equals negative the partial derivative of f with respect to y of xyz over the partial derivative of f with respect to z of xyz. With our function, the partial derivative of z with respect to y equals negative 3z squared plus 3x squared y squared all over x plus 6yz minus 5. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you and good luck with your studies.